All right, so in this video, we're going to look at periodicity and PES. Periodicity is going to be those the 5 main periodic trends: atomic radius, ionic radius, electron affinity, ionization energy, and electronegativity. And then PES is going to be this photoelectron spectroscopy. All right, so first I want to touch on a few terms related to the last video on electron configurations. The first of those terms is paramagnetism. Paramagnetic species are going to be attracted by magnets, and they're created when there are unpaired electrons present in an atom. So for instance, if we're looking at this configuration here, this d orbital, there are 2 electrons that are unpaired. So this species would be paramagnetic. On the other hand, diamagnetism or diamagnetic species are going to be slightly repelled by magnets, and they are formed when all of the electrons are paired in the atom. So for instance, if we're looking at neon, pictured here in its full electron configuration, we have, or the orbital notation of its electron configuration, we see that all of its electrons is paired. Then we also have what's called isoelectronic species. These are going to be species that have the same electron configuration. So for instance, if we are looking at neon, neon's electron configuration would be 1s2, 2s2, 2p6. That would have the same electron configuration as oxide, oxygen with a 2- charge. And then that would be the same too as fluoride, fluorine with a -1 charge, and then same too as sodium plus and Mg2 plus. So all of these species here are going to have the same electron configuration. All right, so next we're going to jump to periodic trends. So quick overview of the development of the periodic table. Dmitri Mendeleev first proposed or arranged the elements in the periodic table by increasing atomic mass. Doing so allowed him to successfully predict the existence of some elements that had not yet been discovered. And however, though, arranging elements by increasing atomic mass did cause some discrepancies. So it caused some elements to fit in families that they didn't really belong in. Moseley, on the other hand, arranged the periodic table by increasing atomic number instead, and doing so fixed the discrepancies seen in Mendeleev's table. And arranging elements in order of increasing atomic number allows us to see a periodic repetition of various chemical and physical properties. And it allows us to also see these trends listed on this slide here, but we are going to focus on these first 5. All right, so when we are looking at these periodic trends, we need to understand the definition of the trend. We need to understand how the trends are going on the periodic table, so whether it's like increasing to the right or decreasing to the right. But most importantly, we need to understand why the trend is going the way it goes. And one of the explanations we'll use in our explanations for why the trend goes the way it does is this idea of effective nuclear charge. So essentially, effective nuclear charge is going to look at the attraction between the nucleus, right, with those positive protons, and the valence electrons in an atom. Okay. So effective nuclear charge, you might see be represented with ZeFF. A lot of times we'll represent the charge of a nucleus with Z, and so then ZeFF just tells us it's the effective nuclear charge. So we have this nucleus that has these protons in there, so the nucleus has a positive charge. That positive charge is going to be attracted to those valence electrons that have a negative charge. However, in between the nucleus and those valence electrons are what we call core electrons. And those core electrons shield the attraction between the nucleus and those outer valence electrons. And that's what effective nuclear charge looks at. All right, so say for instance, we're looking here at sodium. So sodium has 11 protons. And it also inside the nucleus has neutrons, but we're not worried so much about those neutrons because we're just looking at the charged species. Sodium also has 3 principal energy levels, or if we were drawing the Bohr model, it would be represented as 3 rings around that nucleus. In the first energy level, we have 2 electrons. In the second principal energy level, we have 8, and then in the outer one, we have 1. And again, how you can get those is if you write out the full electron configuration, we see that the first principal energy level has 2 electrons. The second one has 2 and 6 or 8, and then the third one has 1. All right, so to determine sodium's effective nuclear charge, we would take the charge of the nucleus, so 11, and then minus the charge from all of these core electrons. So these core electrons are like shielding the pull of that nucleus on the valence electron. They're kind of like blocking that pull. So 11 minus, there's 10 core electrons, 10 electrons in between the nucleus and that valence level. So that gives sodium an effective nuclear charge of 1+, okay, or +1. All right. The trend for effective nuclear charge across the period is that it increases. So increases across the period. And the reason is that you're adding in more protons as we move from left to right without adding in any more core electrons. So for instance, if we're looking at lithium, lithium would have an effective nuclear charge of +1. And again, we can get that because inside lithium's nucleus, we have 3 protons, and then again, some neutrons. And it has, around lithium, there's 2 principal energy levels. The first one, there's 2 electrons, and then in the last one, there's 1. So lithium's effective nuclear charge would be 3 minus 2 would give us a +1. If we were to then compare something in the same period as lithium, so say for instance beryllium, beryllium is going to have 4 protons in its nucleus and also 2 principal energy levels, 2 in the first one, 2 in the outer one. So 4 protons, 4 minus 2 core electrons would give beryllium an effective nuclear charge of +2. So we can see here, beryllium has a greater effective nuclear charge than lithium because we've added in another proton without adding in any more core electrons. Now, that's going across a period. So going down a group, the effective nuclear charge doesn't change that much. It does increase slightly because as we go down, the larger cores are going to be less effective at shielding, but typically we use effective nuclear charge to explain trends across a period. All right, so our first trend is atomic radius. Atomic radius you can think of as the size of a neutral atom. Atomic radius is going to increase to the left and down. Okay. So if we think about why is it increasing to the left and down, so let's start with why is it increasing to the left? Again, let's take, for instance, the lithium. which had 3 protons. Oh, sorry, too many rings. Lithium, which had 3 protons, 2 energy levels. And then beryllium, which had 4 protons, 2 energy levels. 2, 1, 2, 2. All right, so lithium has an effective nuclear charge, we said earlier, of +1. Beryllium, on the other hand, had an effective nuclear charge of +2. So what this tells us is beryllium's nucleus has a greater attraction to its valence electrons than what lithium's nucleus would have for its valence electron. So since we're increasing the attractive forces between the nucleus and the valence electrons as we move to the right, because remember, effective nuclear charge increases to the right, so we're increasing that attraction, so that causes that nucleus to pull those valence electrons in a little closer. So since they're pulled in tighter, that decreases the size of the atom. So this would cause lithium to have a larger atom than beryllium. So that's why it increases going to the left. And then the reason for why it increases going down, we are adding on more principal energy levels. And as you add on higher energy levels, the higher energy levels tend to be larger orbitals. So that's one reason for why we're increasing the size of the atoms as we move down a group. And additionally, as we're adding on more energy levels, we added more core electrons, which shield that valence electron from the nucleus's pull. So it causes the atoms to be larger as we move down. All right, so again, the reason it increases going down is we have higher energy levels that have larger orbitals. And there's also shielding between the core electrons that are blocking the attraction of the nucleus to the valence electron. So it causes the atom to get bigger. Another reason too you could use with this is that you're adding on more electrons into the valence level, so it's repelling. You're adding on more electrons and it's repelling the valence electrons. So that causes the atom to get larger too. Now, as we are looking to the right, again, when we're moving to the right, we're increasing effective nuclear charge, which decreases the size of the atom. So it gets smaller moving to the right, or larger moving to the left. All right, so that was atomic radius. Ionic radius is going to be similar to atomic radius, but instead of looking at a neutral atom, we are looking at an ion. So ionic radius is going to be the size of an ion, something that has a charge. And its trend is going to be just like the trend of atomic radius, and for the same reasons. And before we get into that trend, a couple notes. So one, cations are going to be smaller than the original atom. And the reason for that isn't because you're losing mass, because remember, we're talking about losing electrons here. And the size or the mass of an electron is so small that we generally disregard it. So it's not because you're losing mass, but rather, let's say for instance, we're looking at sodium. Sodium, again, has 3 principal energy levels, and we got 2 electrons in the first, 8 in the second, and 1 in the third. So if we were to look at sodium becoming an ion, when sodium forms an ion, it loses that valence electron. So if we go back here, sorry. When we lose this valence electron, now this entire third energy level is empty. So that would cause Na plus to be smaller than Na. All right. Now, on the other hand, when we gain electrons and form anions, the anions are going to be larger than the original neutral atom. That's because when we add in additional electrons, we increase the electron-electron repulsion, which causes the radius to increase. All right, so again, ionic radius is the same trend as atomic radius, but again, we're looking at an ion instead of an atom, and it's going to increase to the left and down for same kind of reasons. As we're moving to the left, the effective nuclear charge decreases, so it increases the size of the ion. And as we're moving down, we are adding in larger energy levels, and the valence electrons are shielded from the nucleus's pull by more core electrons. All right, so that was the two radii trends. The third trend is ionization energy. So ionization energy is how much energy is required to remove an electron from an atom. So these are going to be positive energy values. You have to put energy into the atom to remove away or to remove its electron. So this trend is going to increase up and to the right for similar kind of reasons as the radii. So as we're moving to the right, we're increasing the effective nuclear charge. So there's a greater pull on that nucleus to the valence electrons. So you would have to put more energy into removing one of the electrons. And then as we're moving up, we're decreasing the size of the atom. So there's a greater attraction from the nucleus to the valence electrons. Now, with ionization energy, you can have multiple ionization energies associated with atoms. So the first ionization energy is going to be how much energy is required to remove the first electron from an atom. And then the second ionization energy would be the energy required to remove the second electron, and then so on. So again, our first ionization energies are going to increase up and to the right. It increases going across because, again, you're increasing the effective nuclear charge. So there's a greater attraction from that nucleus to the valence electrons. So it's going to hold on to it more tightly. So you're going to have to put more energy into removing one of those electrons. And then it increases going up because we're looking at smaller atoms. So the smaller the atom, the closer the valence electrons are to the nucleus. So the stronger the attraction from the nucleus to the valence electrons. So again, you'd have to put more energy into removing the valence electrons from a smaller atom. All right. Sometimes, because I mentioned first, second, and like so on, ionization energies, sometimes you could be given a table of ionization energy values and be asked to identify several things. Like, for instance, they could give you unknown elements, so they're not telling you the identities of the elements, but they could give you the first, second, third, and so on ionization energy values and ask you, like, how many valence electrons does this element have? Or what group is this element in? So ask you some information related to the number of valence electrons it has. So when you see a table like this, there's a couple things that you should notice. The first is that each successive ionization energy is always going to require additional energy. So if we go back, we see that for this first one, sodium, or actually let's jump to phosphorus. Each additional ionization is going to require more energy than the previous one. Okay. The second thing you should notice is that there's a huge increase in the energy that's required for one of the subsequent ionizations. And where you see that huge jump, that's related to the number of valence electrons that element has. So for instance, if we're looking at sodium, we see a huge jump from the first to the second ionization energy value. It's almost 10 times as much energy to remove the second electron compared to the first one. For magnesium, we see there's a huge jump from the second to the third ionization. Aluminum, we see a huge jump from the third to fourth. Okay, so again, that huge jump is related to the number of valence electrons these elements have. So for instance, if we're looking again at sodium, it has those 3 principal energy levels. If we are taking away that first electron, now we are moved into a closer principal energy level. So once we remove this first one, now we're trying, for the second ionization, we're trying to remove one of these electrons from the second principal energy level. That principal energy level is a lot closer to that nucleus. So since it's closer to that nucleus, there's a greater attraction from the nucleus to those 8 electrons here than there is from the nucleus to that 1 valence electron, because those 8 are a lot closer to that nucleus. So it's going to require more energy to remove one of those 8 than it does that 1. So where you see that huge jump, that tells you you've moved from that outer energy level now into a closer energy level. So it tells you how many valence electrons they have. Okay. And if we were to look too at the effective nuclear charge, we're going to see that as we are moving from each subsequent ionization, we're going to see our effective nuclear charge is going to increase. So for sodium, we would have, let me do this. We'd have 11 minus, if we're taking away that first, or that outer 1 valence electron, we would have 10 core electrons there. And so it would have a effective nuclear charge of 1. However, if we look at the second ionization, we still have, so now we're looking at Na+, there's still 11 protons in that nucleus, but now that we moved in a level, we have 2 electrons shielding those 8. So then that's going to give an effective nuclear charge of 9. So again, moving in another energy level, it puts those electrons closer to that nucleus, which is going to increase the attraction between that nucleus and those electrons, which means you're going to have an increase in ionization energy, a huge increase when you're moving from the valence shell to another new inner level now. All right. So that was ionization energy. The 4th trend is electron affinity. And electron affinity is how much energy is released when a gaseous atom gains an electron. So in these cases, since it's energy being released, these values are going to be negative. And these trends, or this trend, is going to increase up and to the right. So same kind of pattern as ionization energy, and for similar reasons as well. All right, so in general, the trend again increases up and to the right, and as we're moving to the right, we are increasing the effective nuclear charge of those atoms, and that causes a greater attraction from the nucleus to valence electrons. So more energy would be released in general as we move to the right when those atoms gain an electron. And then as we're moving up, the size of the atom is getting smaller, so those valence electrons are closer to that nucleus, so there's a greater attraction there. All right, so 5th trend is electronegativity. This trend is important because it explains things like polar and nonpolar molecules. And electronegativity is the ability of an atoms to attract electrons in a chemical bond. And this trend, just like ionization energy and electron affinity, is going to increase up and to the right. But make sure you understand too, we're stopping at fluorine, with fluorine being the most electronegative. The noble gases won't have electronegativity values because they have complete full outer valence levels. So they don't want to gain an additional electron. They're stable. All right, so in general, electronegativity is going to increase up and to the right, with again francium being the least electronegative and fluorine being the most. And for the same kind of reasons, as we move to the right, the effective nuclear charge increases, and as we move up, the atoms get smaller, so there's a greater attraction from the nucleus to the valence electrons. All right, so going back again to ionization energy, when we were dealing with ionization energy, we looked at removing valence electrons, so electrons in the outer energy level. However, sometimes we might want to remove all of the electrons that an atom has. So not just the valence, but the valence electrons and the core electrons. So to move further into the atom and remove core electrons, we're going to have to use waves or radiation types that have a greater energy, right? Because removing a core electron is going to require a lot more energy than removing a valence electron, because those core electrons are a lot closer to the nucleus. So to remove one of the core electrons, we'll want to pick some radiation type that is going to have the more energy, and if it's more energetic, it's going to have a higher frequency. So to remove the core electrons, we're going to want to use X-rays here, since X-rays are going to have the higher frequency values. All right, so when you remove those core electrons, we can generate a spectrum. And this process here of removing core electrons is referred to as photoelectron spectroscopy, or PES, okay? So once you use PES, you're going to get a spectrum, and these spectrums are going to show the total number of electrons if they're giving you the complete PES, the complete spectrum, or they could just show you part of the spectrum that just has one of the specific energy levels. But what these spectrums are going to do is show you the relative number of electrons that are in these different energy levels. So on the spectrum, you're going to have several different peaks, and each of these peaks are going to correspond to a specific sublevel. So if you're looking at the complete photoelectron spectrum, and you're looking at hydrogen or helium, of course that would just have one peak, but if you're looking at anything beyond that, you're going to have two or more peaks. So these spectrums are going to display either signal intensity or the relative number of electrons along the y-axis, and then ionization energy, or it might be called binding energy, or some kind of energy value along the x-axis. And again, each sublevel is going to give its own peak because each sublevel has its own energy value associated with it. All right, so it's kind of similar to mass spectrum. When we looked at that earlier, that's another example of spectroscopy. But in mass spectrum, each peak represented a specific isotope, and in these cases, each peak is going to represent, like I said, a sublevel. All right, so here is an example of a spectrum for boron. And as you can see here, it's giving us, this is the complete spectrum. We have 1, 2, 3 peaks. And we should expect 3 peaks because if we were to list out the full electron configuration for boron, we would have 1s2, 2s2, and then 2p1. So we would expect a peak for the 1s, a peak for the 2s, and a peak for the 2p. Now, one thing with these PESs that maybe could be a little bit tricky, you just got to watch out for, is that often the higher energies will be listed to the left. So along your x-axis, it'll be listed to the left. And then as you're moving to the right, the energy is actually decreasing. So you just got to make sure you're paying attention to the axis they're giving you and the values. So we have 3 peaks on here. And if we want to label these 3 peaks with each of these 3 sublevels, you need to look at the specific energy values. So hopefully you can suspect that this 19.3, the greater energy value peak, would correspond to the sublevel that is closest to the nucleus, right? It's going to require more energy to remove that 1s, which is closest to the nucleus, compared to the 2s or 2p. So this peak here, that is listed as 19.3, is our 1s2 sublevel, or 1s sublevel with 2 electrons in it. This second peak then is going to be the 2s2, and then this third one is going to be the 2p1. And you'll notice too, these peaks here are pretty close to one another in energy values because they're both in the same principal energy level. They're both in principal energy level 2. All right, so if they didn't tell you this was boron, they might ask you to identify the element based on these photoelectron spectrum, and so like you can get the peaks just by going in order, but to determine the number of electrons in each of these peaks, you'll want to look at the heights of those peaks. So if we're first starting with our 1s peak, we know that this 1s had to be filled because we've already moved on to a second peak. And from here, if we look at this first peak, which we know is filled, so 1s2, and we compare it to the second peak, these peaks here are the same height. That means they have the same number of electrons in these sublevels. So this means there's 2 electrons and 2 electrons. And then this third peak here isn't as tall as these first 2 peaks. That means there's fewer electrons in there. And it's approximately half the size of these other 2 peaks. That means there should be half the number of electrons in this third sublevel, which in this case there is. There's just 1 electron in this 2p here. All right, so let's compare then 2 different PESs for lithium and boron. So let's compare lithium spectrum to borons. Lithium, if we were to list out its electron configuration, is 1s2, 2s1, and then boron is 1s2, 2s2, and 2p1. All right, so again, if we were to kind of label these peaks with their specific sublevels, for lithium here, the higher energy, we're going to have 1s2, and then we see that this is our 2s, so we know there's only 1 in here because it's half the size of this first peak. All right, and then boron, again, we labeled it in the last slide, or a couple slides ago. All right, so comparing those, again, we would expect that lithium would have 2 peaks because there's 2 sublevels. Boron, we would expect there to be 3 peaks because there's 3 sublevels. Now, some questions you might see would be to compare the peaks associated with their relative or their specific sublevels. So what I mean by that is they may ask you to compare the 1s sublevel of lithium to the 1s sublevel of boron. Now, when you are comparing those two, they might say, why does boron's 1s2 or 1s sublevel require or have a greater binding energy than the 1s sublevel for lithium? Now, think about why would it take more energy to remove the electrons in the 1s sublevel for boron compared to removing the electrons in the 1s sublevel for lithium? Now, to do that, let's look again at what's different between those 2 atoms. So lithium has 3 protons in its nucleus, 2, 1. And boron has 5 protons in its nucleus. Both of them have the same number of principal energy levels. So there's the same number of core electrons in each, but since boron has 2 more protons in its nucleus compared to lithium, boron's nucleus has a greater attraction for its valence electrons and even these other electrons here too, its core electrons, than what lithium would. So since boron has more protons in its nucleus, a greater nuclear charge than lithium, there's greater attractions for boron's nucleus to its electrons compared to lithium. So it would require more energy to remove the electrons in the boron atom. All right, so besides them giving you the peaks and asking questions about it, oh, another note too is sometimes the peaks might be split up instead of one long peak. But sometimes they might give you a peak and ask you to identify the element. So take a second, look at this peak, and try and identify what the element is. So if you still need more time, you can pause the video and identify the element. But if you're having trouble getting started, I would start, in this case, on the left side, where we see we have the greater binding energy. From there, you know that the greater binding energy is going to correspond to the sublevel that's closest to the nucleus. So we're looking here at our 1s sublevel, and we know that this 1s sublevel had to be filled because we've already moved on to our second sublevel. So we're going to assign this as 1s2. So our second sublevel we would fill is a 2s. And this 2s we know had to also be filled because we've moved on to the third sublevel. So we give this a 2s2. So our next sublevel is going to be a 2p. Now, from here, we don't have any peaks after this, so we can't automatically assume that it's going to be 2p6, that this is full. Instead, we'll have to compare the heights of the previous peaks that we knew were filled to the height of this last peak here. So comparing those peak heights, we see that the 1s and the 2s, which both are going to have 2 electrons in them, have a height that is 2 lines high in this case. So in this case, 2 lines is giving us or representing 2 electrons. So one line is 1 electron. So if we were to compare, or if we were to count the lines that this last peak here is tall, we would have 1, 2, 3, 4, 5, 6 lines tall. That means there are 6 electrons in this 2p. So in this case, this 2p is filled, but you would still have to count or compare the height of this final peak to the previous peaks. And that should make sense too, because this peak here is 3 times the height of this prior peak, so there should be 3 times the number of electrons in that peak. So now from here, once we have labeled our peaks, we have the electron configuration as 1s2, 2s2, 2p6, and that would give us neon.